Hello, this is part 4, I believe, of the AC Basics videos, and this will probably be the final part of the basics, and then we'll start with the inductors section, part 1, and kind of go from there, although we're still going to be talking about AC circuitry. So, in the last video, we talked about how that an alternating current was generated through the use of magnetism, and we talked about how a voltage is generated in a conductor when the conductor cuts through lines of magnetic force, represented in my little diagram here by the horizontal lines. So these are the two poles of a magnet. We have a big loop that's spinning around inside of this magnetic field right in the middle. Up here at the 0-degree point, the conductor, which is represented by the little dot there, is running parallel to the magnetic lines of force, so it's not cutting any lines of force, and there's a minimum voltage generated. As it spins 90 degrees to this point right here, it's now running at a right angle to or perpendicular to the lines of force, cutting the maximum number of magnetic flux lines, and thus generating the maximum or peak voltage in the positive direction. Then it slowly decreases as it's rotates further to the 180-degree position, and then goes into the negative peak voltage in the opposite direction at 270 and back to 0 to complete a full cycle of AC. And we talked about how that we could represent this graphically by drawing a sine wave where the horizontal line represents the degrees and the vertical line represents the voltage quantity of the signal that's generated. And then finally we talked about how that we had to find some practical value that we could use, since the AC voltage changes at each instant as it makes its rotation or throughout the sine wave. And we talked about how you could find the RMS value by taking your peak voltage, which in the example we used here, it peaks out at 140 volts, and multiply that by 0.707 to get a DC equivalent voltage. This is called the RMS voltage. And then finally we reviewed our rules for series circuits, and we showed how you can plug in that RMS voltage value to solve a circuit using Ohm's law, in much the same way that you would using Ohm's law in a DC circuit. So in this video we're going to finish all of this out. We're going to use the RMS value, or it's not really the average value because there's another value that's actually the average, but this root mean square value is essentially an average value in the sense that it's a constant number that we can use that would actually be represented on this graph as a straight line. In other words, we could find 120 volts on here and just draw a straight line, and that would be our RMS equivalent value, or our RMS value that's would be equivalent to the DC value. Okay, so now let's look at a parallel circuit real quickly to see how this works out. Give us a chance to review our rules for parallel circuits real quick. And then we're going to start to talk about an exciting concept, at least it's exciting to me. I guess it's all relative, but anyway, induction. And induction is something that we can take advantage of with AC circuits that really is not that useful with DC circuits. We're going to take advantage of the fact that in AC our voltage and current are always alternating or changing their polarities. So and keep in mind, I don't always use technical jargon because A, it's hard for me to remember all the technical jargon, and B, because it just makes it more confusing. I'm coming at this as sort of an amateur, so but hopefully it's helpful, and I don't know, for people that are interested. So, okay, let's look at this parallel circuit real quick. And remember that a parallel circuit, the advantage of a parallel circuit a lot of times is that over a series circuit is that now instead of just having one path for current flow, we actually have multiple paths. If you think way back to the Christmas lights example that I used, if you had seen that video, we talked about how that if you have one, let's say that these resistors here represent light bulbs, and let's say that one of them burned out. Well, if this was a series circuit, we'd be up the creek, because if there's only one path for current flow, and you have to have a path for current to flow for it to flow, then that one light bulb going out would stop electricity flow to the other light bulbs. But here, because we have multiple pathways, those other pathways will still provide a path for current flow, so that's one of the advantages. Now, we can use this RMS value. So I have 120 volts, which is the RMS value that comes out of your wall socket. It's actually produced, if you remember, from a constantly changing signal that reaches a peak of about 169.7 volts, and then it reaches another negative peak of 169.7. Well, we found that the RMS value of this wave is 120 volts. So we can use that RMS value to solve for our parallel circuit, especially if it's just got resistance in it, as this one does. And so we're going to use our Ohm's law formula again, but this time one thing is going to change, actually a couple of things. For one thing, the current isn't necessarily going to be the same in all of the branches, but today we're just going to solve for the total current, since I've already covered how to solve for all these different values in a parallel circuit. But do keep in mind that the current in a parallel circuit is not the same, but usually is the sum of the individual branches. Also keep in mind that even though we have three resistors here, the total resistance value should be less than the sum of all three of these, or even any individual resistor, because we've provided multiple paths for current flow. So in essence, we've reduced the overall resistance, and we're going to have to use the reciprocal of the reciprocal formula to solve for our resistance. So let's do that quickly so we can get on to induction. I rearranged the Ohm's law formula as I did in the previous video, and I have the I, which represents current amps, and that's the value that I'm solving for. I have E over R. E represents the voltage, and R represents the resistance measured in ohms. To find that, I'm going to add the reciprocal of my resistor values here. I have a 100 ohm resistor, a 50 ohm resistor, and another 100 ohm resistor. So I plug that into my formula, add it all up, and it comes out to 25 ohms. Now, because these resistors are all similar, in other words, they're multiples, I can actually simplify this a little bit, and I could have taken that middle resistor and made it basically made it into two equivalent resistors. So I could say, well, you know what, in a parallel circuit, if I had two parallel branches that had a 100 ohm resistor in each one of them, that's the same thing as one branch that has a 50 ohm resistor. So another way I could have solved for the resistance in here was to take the number of resistors, if I used an equivalent resistor of 100 ohms and made this into two branches. So I would have four, instead of having two 100 ohm resistors and one 50 ohm, I could treat this as if it were made up of four branches, and each branch had a 100 ohm resistor. Then I could just divide that 100 ohms by the number of resistors, 4, and it would still also give me the resistance value of 25 ohms. Okay, I found that now. I'm going to plug it into my formula. We're going to use the RMS value of 120 volts, and we're going to divide that by 25 ohms, and I find that my current is 4.8 ohms. Sorry, amps. Okay, so in essence, what I've done is I've just used, even though this is an AC signal, or it's an AC fed circuit, and even though the AC signal is always changing its voltage over time, we came up with what is called the RMS, or root mean square value, which is kind of like an average value that's constant. In other words, it doesn't change, that we can use to solve for our missing values or our unknowns in a given circuit. In this case, the missing value was the current. We didn't know the current, so we had to solve for that. Okay, now that we've sort of talked about how we can use the RMS value to solve in an ohm and plug into the voltage for Ohm's law to solve for current or resistance, we could have also solved for resistance had we known, say, the current flow. Now I want to talk about a couple of concepts or a couple of things that are really important in AC electronics, but not so important in DC circuits usually. There's some exceptions, but generally speaking. And these two concepts, one of them is called inductance and the other is called capacitance. And I believe that we are going to, I want to start here with the first of them, inductance, and we're going to talk about that. Now this all gets back to what I was talking about in the last video. We said that if I had a wire, okay, let's say this is a wire, and where am I? Okay, this is a wire that I have in my the red marker, and this black marker, the marker with the black lid, is a magnet. If I move the conductor up and down so that it's crossing the invisible lines of magnetic force generated by this magnet, that's going to generate a voltage. And if it were a closed path or closed circuit, we would have current flow. Or I could move the magnet. Either way, I have invisible lines of magnetic force that are cutting through the conductor and generating a voltage. This is a process that's called induction. A corollary to this is that if I have a conductor and I have electricity flowing through my conductor, let's say that it's flowing in this direction, that's also going to generate a magnetic field. So magnetism and electricity are very interrelated. So as I have current flowing through my wire, that's going to cause a magnetic field to expand out from the center of the wire, and it's going to sort of rotate around the wire like this. Okay, that's important. That's an important concept, and it has to do with the use of inductors, which we're going to begin to talk about a little bit right now. So let me see here. In the preceding examples that I had, we were just using resistors, and so we could actually use the Ohm's law formula as I had written it, E equals I times R, to solve for the missing values and plug in our RMS constant voltage value to solve for those unknowns. But as I said, we're going to talk about a new concept, inductance, and it gets back to this idea, and here I've drawn a picture of this. So if we have a piece of wire, this little tube thing here, ooh, there it is, represents a wire, and the little dotted lines, I don't know how well you can see that there, but the little dotted lines represent the invisible lines of magnetic force that expand out from the conductor as current flows through this. Now, what happens in a DC circuit is, since the voltage is constant and the current only flows in one direction, as soon as you close the switch, as soon as you close the switch so you have a complete path for current flow, at that instant currents are going to begin to flow, and only in one direction, and it's going to rapidly rise to its, almost instantaneously, rise to its maximum value. As it does this, a magnetic field expands outward from the center of the conductor and eventually even expands out beyond the conductor and rotates around it. Now in a DC circuit, this magnetic field will maintain itself in the expanded or maximum position where it's rotating around the conductor until we open the switch, and then once there's no more current flow, then the magnetic field will then collapse in upon itself, and in other words, the magnetic field is related to the current flow. Well, that's not such a big deal in a DC circuit, but it has some interesting properties associated with it that we can take advantage of in an AC circuit. And one thing that is, you kind of have to keep these two concepts in mind. If I have magnetic lines of force and they cut across or move across a conductor, that generates a voltage. But I also generate a magnetic field around a conductor whenever current's flowing through the conductor. Well, we can put those two concepts to use and take advantage of this phenomena that's called induction to limit current flow in a circuit. So let's talk about that a little bit. Okay, so let's say that now I do not have a DC circuit, but I have an AC circuit, where the current flow changes polarity or directions at each instant. One instant it's flowing this way, the next instant it's flowing that way. What does that mean then for this magnetic field? That means that the magnetic field is constantly expanding outward, reaching some maximum value, and then collapsing back down in on itself, and then expanding outward again to a maximum value as the current is changing directions. Because remember, with get the other picture here. With an AC circuit, and this I think I have it upside down. There we go. This line in this particular diagram represents voltage, but it could just as easily represent current flow, because current flow is proportional to the voltage. So as the voltage increases, the current flow is also going to increase, which means that if we have just a straight conductor at 90 degrees, our current flow is going to be at a maximum in the positive direction, and we're going to have a magnetic field that's fully expanded around the conductor. Then the current is going to begin to decrease back down to zero, and that magnetic field will collapse. And then it will expand in the opposite direction, having an opposite polarity, and the magnetic field will expand outward from the center of the wire once again to a maximum value, and then collapse in on itself, or collapse again as the current goes back down to zero. Well, keep in mind that as what did we say about magnetic lines of force crossing a conductor? It generates a voltage. And in this case, the same thing is true. As this magnetic field expands out from the center of the conductor, it's crossing the conductor itself, and so it generates, in essence, a voltage. It induces a voltage in that wire. Okay, that's called self-induction. And then as the current changes directions again, the field collapses, and then guess what? As it collapses, the magnetic lines of force cross through the conductor once again as it collapses back in upon into the conductor, essentially. So that induces a voltage. Well, we can take advantage of this process to control our current flow in the circuit. And what we're going to do is take this conductor and wrap it into a coil. Now we can take advantage of the fact that as the magnetic field expands, as the current increases to a maximum in one direction, that expanding magnetic field is cutting across the conductors in the coil. Okay, and then as it collapses, it cuts through the conductors again. Then it expands in the other direction, cuts through the conductors again, collapses and cuts through the conductors again. And what this is doing is generating a voltage, which is referred to as a counter EMF, a counter electromotive force. But guess what? That voltage that is induced in the conductor has a polarity that is always opposite to that of the source voltage. Okay? And I think I have a diagram of this, maybe my last one that I can get in for this particular video. Okay? So here is my, it's hard to see here, but let me see if I can, Okay, here's my circuit. This is an AC circuit. The only thing that I have in it right now is a coil. Okay, when the voltage starts to flow in one direction from the source, this is called the applied voltage. As the current passes through the coil, it's going to induce a voltage in this coil that has a polarity which is exactly the opposite or out of phase with the applied voltage. Now, the effect of all of this is that it opposes changes in current. So in other words, as the current grows in the first part of the cycle up to its maximum at 90 degrees, this induced voltage is actually trying to oppose that increase in current. And then as the current collapses back down to zero or falls back to zero, the induced voltage, still with an opposite polarity, tries to maintain the current. In other words, the induced voltage from the coil opposes any change to current flow in the circuit whatsoever. We can use this concept much like a resistor. I think I'm about out of time, so I'm going to have to close this video. We'll pick it up in part 2 of inductors.